Okay. Hello guys, welcome to this series of graph revision of graph DSA. So in this series we will be revising every graph concept that we learned. So what all we will revise in first few lectures are like we will start from the very much basics, like what are the graph data structure and how do we do DFS, like where we will find a path from source to destination, whether it exists or not, and we will also find all the paths. Then we will also be finding like connected components of a graph. We will look into whether a graph is connected or not. These are pretty much concepts that we will be revising in first few lectures. Like we will also find number of islands in a graph. These are all like basics of graph. This we will do it for a warm up, and then there will be a second series in which we will cover the uh, advanced lectures, advanced concepts of graph. Like we will be solving problems and also we will be learning concepts. And in this series what we will do is we will break down every problem into simple patterns that we can remember, and we will try to remember those in a way that we won't forget, so we don't have to do revision again and again. Of course there will be few problems which do need revision because they are not intuitive. Few problems they are very intuitive. You know the basics, you start from the basics, and it just when you iterate on the basic approach you'll get to the result. But few problems the answers are in a such a way that you need completely different approach, some kind of mathematical, some kind of different approach, so which you can't intuitively get there, right? Those we need to remember, and we remember in a way that we can retain it for a very long time. Okay, without wasting time, let's start with the very first basic thing. What is a graph data structure? You can skip this video if you already know and have solved a bunch of problems recently about graph, but I would recommend to please continue this lecture, because if you understand this concept, like there will be a lot of questions you will be able to do intuitively, because fundamentals, if you have a very good grip on fundamentals, the questions you can do on your own without even revising. Okay, so let's start. Very simple question. What is a graph data structure? Very basic. Let's say we don't have any understanding of what a graph is, but if I have to define it, there is no definition for a graph structure. It's just a description on the basis of how we use it. It's very personalized, right? So how I can define a graph is something that has nodes. Okay, let me grab a pointer. Okay, so how will I define a graph data structure? Something that has vertices or nodes, just like this. These are vertices or nodes, or we can call them cities, some kind of points. We can call them anything. In a problem, it can come as a cities, it can come as a number, cell, grid, it can come as anything. The moment you see connection between those, like you have to travel from one to another, you have to travel from one to any random one, any random other vertex or node, that will become a graph. How? Like this. Here these are vertices and we join them, and it has some weight. It might also have some direction, like we can travel only from this city to this city via this road, but the distance is 40 kilometers. So this is like kind of structure where we can use a graph data structure to represent this kind of structure. So this is graph. Next thing, what are the real life situations of this? Like um, when we have to reach from a city X to city Y, let's say from Bangalore to London. So what are the ways? Like let's say if I consider this city as Bangalore and this city as London, we can go this way, we can go this way, or we can travel from this way or this way. So there are four ways which I have written here. So there can be multiple questions on this structure. Like if I want to ask you that shortest path, like very shortest path in terms of distance to reach Bangalore to London, you will say this, right? And if I say the cheapest path, like obviously this is 40 kilometers, this is 2 kilometers, and this is 8, right? But these are like less number of stops. And if I say I have to optimize on the money I travel with, so what I will do, I will just take this path. This is apparently the longer one, but it is cheapest in terms of distance. So we can also, there might be questions on like minimum spanning tree, like it's a word you might have heard it if you have solved graph problems earlier. Minimum, like it's the minimum roads we need to connect these two cities. Let's say there are cities, a number of cities, and there are no roads on it. But if we are asked to build roads with minimum amount of material joining all such cities, what we will use, a concept called minimum spanning tree. Basically it's Kruskal's minimum spanning tree. We will learn about it in later videos. And there is like Prim's algorithm, Kruskal's algorithm for the same. And there is, and let's say we have one more situation, common situation, like we have files. Every day we write code to compile something. Well, we write code to um, build any application. We have files, and we import other file stuff into our current file. So if I ask you how, what is the order in which you will compile the files such that the compilation is doesn't give an error, like you will start from the file which has no dependencies, and you start compiling in the order of it, right? Let's say f1 depends on f2, so you will compile f2 first, then you compile f1. If f2 was depending on f3, you will compile f3 first, and then f2, and then f1. This is the order of compilation. So this dependency between different files and connection between those can be represented in a structure of graph. Okay. And next thing is how to represent this graph data structures efficiently, right? So we have multiple representation of it, like this one. So if you are able to see here, the first one, this is a graph and we can represent it in multiple representation. First one is adjacency matrix, where we have these nodes plotted in a 2D array, and we just mark one if there is an edge between A and C, right? And there is, there is an edge between C and between A and B, and there is, this should slide a bit. Okay. And the space complexity of this representation would be, which since we are storing, let's say there are like v number of vertices, and we need v into v, that is v square number of cells or bits to store that. This will be very good if you want to scan, like query an edge, whether there is an edge between A and B, just query it in O of 1 operation. And or if you want a neighbors of a node A, like a city, you can query it in a O of V, that is scanning the entire row. You'll get all the neighbors of A if you scan this row. Okay, that is like you will get B is a neighbor, then E is a neighbor, and F is a neighbor. You can see it. Then it comes, where does it break is when you have like, it's very good if you have a dense graph. Let's say you have 100 nodes or 100 cities, and you have to do a very large number of connections between those cities are, and it is a very good data structure to use. Also where the DP, or where edge query is used a lot and DPs are used. This is like Floyd-Warshall kind of DP algorithm or a representation. Here we can use this structure and this proves very efficiently. But when you have like 10k nodes, more than 10k nodes, it breaks. Why? Because let's say you have 10 to the power 6 number of nodes, which is maybe you will have if you are building a social media application. Like one person has like, there are like 10 million plus users, so you will need how many? you will need 10 to the power 14, double of that, square of that. 10 to the power 7 into square, that will be 10 to the power 14, that is 100 TB of storage just to store this graph. So it breaks there. Next we can do is edge adjacency list. What we will do, we will just take this A and we'll just store all of its neighbors in a list against it. And next thing what we can do is also good. This like space will be it takes less space, but edge query will be a degree of u, that is nothing but the number of neighbors of any node, and all neighbors is the same degree of u. And adding vertex is very easier here. You just append, if you are adding a new, you will just append one item and you will make a list, or whatever edges are there, you just fill the list out of it. And next thing is you can just store the purest memory, not the purest, like it's as exactly as can possible, minimal space for storing all this. You just store them as connections, like a comma b, then a comma f, like this. This is also good, like kind of, this is used mostly when you have to do minimal spanning tree. You have to sort these edges based on the weights or something. It's like critical MST. We will learn about it in the coming lectures. And there is one more. This is like we won't be using it in our DSA practice a lot, but this is very useful if you want to cache the graph in Redis or something, because you compress all of them having like 1 or 2D array kind of thing, like two-dimensional structures. This is like two one-dimensional structures. These are very cache friendly. And the way we will look at the code, like how to write it. Basically it's just, if you want to query like what are the A's neighbor, A is let's say 0th node, right? So what I will do, I will take row pointer of 0 and row pointer of 0 plus 1, that is 3. So 0 to 3 minus 1, so these three are my A's neighbors. So this is how we store it. Less important for DSA, but very important if you want to cache the graph. We will learn about it in coming lectures. I will be showing you the code, how to do it, and where exactly this is used. And then comes the incidence matrix. All this representation, we were using nodes as a first class citizen, like we were storing nodes, and connections were calculated or represented in a way that we have to traverse the via, we have to get the edge. We were querying edges by storing nodes and connections. Here what we will do, we are directly storing the, we were treating edges as the first class citizens. Let's say there are 7 edges here, 1 2 3 4 5 6 7, right? So we store them, and we have a 2D matrix of edges cross nodes, and we just mark one where each edge, like if I want to know what edge 0 has, it has a connection between A and B. Very simple, right? But not so efficient for sparse graphs. Sparse is like a huge large graphs of very distant connections. For dense graphs it is good. It's basically used in Kirchhoff's law, like circuit analysis and graph theory, and also computation, like GNN, Laplacian matrix and all. Less important for DSA practice, but important in areas of like electrical circuit analysis and all. So this is about like what our graph data structure looks like, and how, what are the ways we can represent it. We'll also show you the code how to represent it. Like if I run this thing, say graph, I'll just run this thing. So this is incidence matrix, how we store it. 0 comma 1 edge is there, so 0 comma 1 are marked 1. This is compressed sparse row. This is if you want to get a node I, neighbors of node I. So what you will do, you will take row pointer of that I and the next one, and you will travel from here. Let's say it's 0, right? You will from 0 and it's 1. So what you will do, 1 minus 1, that is let's say you want to take here to here, right? That is 1 to 2. So what you will do, from 1 you will go to 4 minus 1, that is 3 here. So 0, 4, 2 are the neighbors of 1. If you want to see, you can see here. See, 1's neighbor are 4, 0 and 2, and it works. And there is also adjacency set. When you want to query whether query edge in O of 1, what you can do, 0, and whether you can whether it has a connection between 1 has a connection between 2 or not, you can just query like adjacency set of 1 and contains 2. You can get it in O of 1. And there is obviously the adjacency list, and there